find the limit x approaches 0 of cosine of x minus 1 over sine of x. That is definitely a 0 over 0 type of limit. If you plug in 0 for x, you're going to get 1 minus 1 over 0. And so what do we do? Well, this is one of those things, again, where it's a trig thing, and there's not a lot of great tips for trig things, but one trig thing we can do here is multiply by a conjugate. So I'm going to multiply the top and the bottom by cosine of x plus 1. And I'm going to get the limit x goes to 0 of cosine times cosine is cosine squared x. The middle terms cancel. Minus 1 times 1 is minus 1. All over sine x times cosine x plus 1. Oh, let me check one. Where's my a couple things here? Sorry, 1 second. There's no one on Zoom yet, which is totally fine. There was something else I wanted, but yeah, that's what I wanted. So cosine squared x minus 1, that kind of looks familiar, but not exactly like what we want it to be. So it is a trig, and it's just not very recognizable. If you change the order of subtraction, or if you factor out a minus sign, if you make this the limit as x approaches 0 of -1 times 1 minus cosine squared x, then it's a little easier to see what's going on. So then 1 minus cosine squared is sine squared. And you can cancel a sine x here with a sine x there. So you're really left with the limit as x approaches 0 of negative sine of x over cosine of x plus 1. And then we can plug in 0, because it's no longer a 0 over 0 type of limit. So we plug in 0, you get negative 0 over 1 plus 1, which is 0 over 2, which is 0. Fun fact, 0 is the only number that is its own negative. Worth knowing, actually. It comes up occasionally. So let's look at another limit. Let's look at the limit. Some limits to infinity. Limit as x goes to infinity of sine x over x. It's a good question. So here's what I would say. Sine x, as x goes to infinity, just sine x, doing this, right? Forever and ever and ever and ever and ever. Are you guys seeing over there? Yeah, cool. You can see over there. Yeah. So if you have, specifically, when you have limits to infinity, or I should say limits involving sine, where the thing you're taking sine of is going to infinity. So like sine of x where x goes to infinity, or sine of 1 over x when x goes to 0. Right? Those are both cases where the thing you're taking sine of is going to infinity in some way, and you can't really see what the behavior is. That's almost always a good clue that we should be using the squeeze theorem, sandwich theorem, whatever you want to call it. So I see limit to infinity, I see sine of x, I'm like, oh, it's probably squeeze theorem. So here's what I'm going to start with. I'm going to say, well, I know sine of x is always between what two numbers? -1 and 1. That's a prime inequality you should keep in mind all the time. Sine and cosine are always between -1 and 1. And then I want to take the limit of sine of x over x. So I'm going to take this inequality and divide everything by x so that I can have a sine x over x in the middle. So I'm going to have a -1 over x less than or equal to sine x over x less than or equal to 1 over x. Cool. And now, for the squeeze theorem, we take the limit of the outer things, the boundary things. So I'm going to say, okay, well, the limit as x goes to infinity of -1 over x. Well, if the denominator is getting really, really big, 1 over the really big number is getting really, really small. It's getting closer and closer to 0. And similarly, the limit as x goes to infinity of +1 over x is also 0. And so then we can say, by the squeeze theorem, the limit that we're taking has to be 0. Limit as x approaches infinity of sine of x over x has to be 0. There's no other choice. And again, if you wanted to, you can graph both things, right? You can graph 1 over x on Desmos and -1 over x on Desmos, and then sine of x over x. You'll see that it's just squished between it the whole way. It gets closer and closer and closer to 0. Okay. Yeah, we should talk about this one for a second. So this is a limit that you may have already talked about in class. I mentioned it briefly a while ago. The limit as x approaches 0 of sine of x over x. So there's a couple ways to deal with it. You could totally do the thing we do in the book, which is where we plug in a bunch of different values of x closer and closer to 0, and you see you get values that are closer and closer to 1. Here's that work. I don't want to write it out. I don't feel like writing it all out. But here's that work right there. If you plug in x equals -0.1, sine of -0.1 over -0.1 is 0.998. When you plug in this number, you get that. Plug in this number, right? You get closer and closer and closer to what appears to be 1 from either side. So certainly looking at this, it looks like the limit's 1. And we could prove it. I feel like as much as I would like to, because I really like proving it, it's like a fun proof to do. I don't think that's the best use of our time right now. So I think I'm going to let it go for the moment. I will say the graph of sine of x over x looks like the following. And again, my picture's not perfect. They're never going to be perfect, but that's the idea. There's some symmetry there. It is symmetrical about the y-axis. I didn't draw it very well, but we can see that as we get closer and closer to 0, the y values do get closer and closer to 1. But it is not defined at 0. If you plug in 0, you get sine 0 over 0, which is totally undefined. So here's a great example of a limit existing, but I'll just point out that, but for f of x equal to sine of x over x, f of 0 does not exist. Totally undefined. So later on, we will talk about how this means the function is not continuous there. It's definitely not continuous there because there's a point. And we'll talk more about the definition of continuity a little bit later. So the reason we mentioned this particular limit is because this limit does come up a lot. So here's what I would say more generally about this sort of limit. The limit as, I'm going to say it this way. Some stuff approaches 0 of sine of that stuff over the same exact stuff, the limit's going to be 1. I'm just writing stuff instead of x. So for example, if I was taking the limit as x approaches 0 of sine of 6x squared over 6x squared, well, it's certainly sine of stuff over the same stuff, and the stuff is approaching 0. Because if x is going to 0, 6 times x squared is also going to 0. So this limit is definitely 1. And there's not a lot of work to be shown here. The expectation is kind of that if you see that you have a sine of a thing over the same thing, and both of those things are going to 0, then that limit is going to equal 1.
We have to show our work on a problem like this.
So let me give you another example for the work you would show on a problem like this. It's not exactly like this. I would say for this, there's really nothing else to do. All you really say is that limit's 1. There's no other work to be done there. Let me show you a slightly more complicated example. Let's say we want to do this. So yeah, let's say I want to find the limit as x approaches 0 of sine of 6x over 4x. So now I have a problem. I have sine of a thing over a slightly different thing, and both those things are still going to 0. This limit's not going to be 1 because those things are not the same. So what do? Well, I like to do what I call the wish method. You take the limit as x approaches 0, and I'm going to write sine of 6x. I'm going to ask myself, what do I wish I had underneath sine of 6x? Right, I wish I had 6x, because that would make it easy. Then the limit would just be 1. So what I'm going to do is I'm going to say, well, I wish I had 6x right there. But I really don't. What I really have in the denominator was 4x. And what I really have in the numerator here is a 6x to cancel out the 6x that I wish I had in the bottom. There are other ways of getting there. This is just the way I've always imagined it, and it seems to work pretty well. So I wish I had that, but now look what I've got. If I simplify this a little bit, I have the limit as x approaches 0 of 6x over 4x reduces to 3 halves. The x's cancel. I have 3 halves times sine of 6x over 6x. The limit of this part is going to be 1. This is going to equal 3 halves times 1, which is 3 halves. Let's do another one. So I want to find the limit as x approaches 0 of sine of 9x over 7x. So what I really do is what I just did. I'm going to break this fraction up into 2 pieces of fractions. I've got sine of 9x over something, and I've got something over 7x. I haven't changed the fraction at all. I've written it in a really stupid way, but I haven't changed it. It's still the same. It's still sine of 9x divided by 7x. And now I'm going to ask myself the same question I asked before. What do I wish I had beneath sine of 9x? Why do I wish that? Well, because I know I need sine of a thing divided by the same thing, right? I can't have sine of something divided by something that's different because I don't know what that limit is. And if I have sine of something that's going to 0 divided by the same exact something that's going to 0, that the limit of that piece is just 1. But then I have to account for what I've done. I can't just divide by 9x. That would be changing things. So I also have to multiply by 9x to make it so it's still the same. And then I'm going to show one more step in this one. So this is equal to the limit as x approaches 0 of 9/7 times sine of 9x over 9x. And if you want, when you have the limit of a constant times a function, you can pull the constant multiple out in front of the limit. It's a totally valid operation. It's one of those limit rules that we briefly talked about. So you can say this is equal to 9/7 times the limit as x approaches 0 of sine of 9x over 9x. And then definitely this limit is 1. So you get 9/7 times 1, which is 9/7. Oh, sorry, so I can do one involving cosine, but it's not going to be nice. And here's the thing. So there is not an analog for cosine x over x. But let's look at an example. So if I said, what's the limit? Sure. We'll go from the right-hand side. What's the limit as x approaches 0 from the right-hand side of cosine x over x? Well, when you plug in 0, what's cosine of 0? 1. 1 over 0 isn't a 0 over 0. It's not one of these indeterminate forms. So I'm going to reiterate. When you have 0 over 0 as your limit form, your answer can be anything, right? That's why we use the word indeterminate. It is not determined what the value is going to be. There are infinite possibilities. On the other hand, in this sort of situation, the only possibility is infinity. See how I switch that around? Right. So, or negative infinity. So when you have a non-zero number over 0, your limit is some sort of thing that's getting infinitely large, or maybe negatively infinitely large. So what's really happening here for cosine x over x is I have values that are getting closer and closer to 1 over things that are getting closer and closer to 0. When you have a fraction where you're dividing by a very small number, the limit ends up being super large. But really, the limit doesn't exist, but it's growing and growing and growing. So I'm going to write a thing, and I'm going to say what it means. So if I was asked what this limit was, I would say it's infinity. But really, what people also say, though, is I would say that this limit doesn't exist. It doesn't exist. There is no one particular value that this function is getting closer and closer to. It's growing. It's getting really big. It's not getting close to infinity. You can't get close to infinity. It's way out there. You can't get close to it. Try. Did I get close to it? No. It's still way out there, right? No matter how far I go this way, I'm not close to what's way out there. You can't ever get close to infinity. So the limit doesn't actually equal infinity. But we use this notation to write what we mean. We're not saying the limit's actually equal. We're not saying we're getting close to infinity. We're saying that as x is close to 0, this expression cosine x over x is just going to grow really large. And it might help see the graph of it. I personally think it almost always helps to see the graph. Let's take a look real quick. I mean, what we're going to see is a vertical asymptote. Oops, okay, maybe if I can get that to go over there. Okay, maybe not. So if we graph cosine x divided by x, right, we see that, oh yeah, as x is getting closer and closer to 0, the values are getting really big, and they just keep going and going and going forever now. So cosine ones like this don't really have a nice kind of result. Couple other things. Let's look at a few more of these, and then we will. Oh, I know what it was though. So, but this kind of thing comes up often when you have other sorts of limits. For example, if I said, what's the limit as x approaches, let's go from the left this time, 0 from the left of, I don't really want to pick 0. I changed my mind. Sorry, apologies. Let's say 10 from the left. How exciting. Of x squared over x minus 10. This is a similar sort of thing where you end up getting, if you plug in 10, you get something not 0 on the top, you get 100, right? So if we plug in, we're going to get 100 over 0. When you get a non-zero thing over 0, that means your limit's either going to be infinity or negative infinity. Or if it's a two-sided limit, it might not exist. Because maybe one side's doing this and one side's doing this, and they're not going towards the same sort of thing. So in this case, all we really have to determine is the thing positive or negative? So this is definitely, I would say this is a non-zero number over 0. And when that happens, there's only 3 possibilities. We either get infinity, we get negative infinity, or we get a does not exist. I'll show you. But yeah, that's a fair question. So in this case, the numerator is positive. And if I'm approaching 10 from the left side of 10, meaning the slightly less than 10 side of 10, is x minus 10 going to be slightly positive or slightly negative? Slightly negative, right? It's like 9.999 minus 10, which is negative 0.0001. That's a very slightly negative number, which I like to write like that, with a 0 with a negative superscript. So if you have a positive number divided by a negative number, the whole thing is positive or negative. Negative, right? It's definitely negative. So what we're going to say is that this limit, as x approaches 10 from the left of x squared over x minus 10, is going to be negative infinity. Because it's a negative number, and again, it's a negative 10, or sorry, 100, apologies, divided by something that's getting super duper small. So the fraction is getting super big. Let's look at the other side of this limit before, and then we can go there. So on the other hand, what if I look at the limit as x approaches 10 from the right-hand side of x squared over x minus 10? Well, now if I'm thinking about plugging in a number that's a tiny bit larger than 10, the numerator is still 10 squared. I'm just going to throw in a straight 10, not like pretend like it's 10.1, whatever. 10 squared. Okay. And then a number a little bigger than 10, minus 10, is a number that is slightly positive, right? It's like 10.001 minus 10. That's a positive number. And sometimes we write this in quotes because you really shouldn't be writing like stuff divided by 100. And then a positive number divided by a positive number is a positive number. This limit is getting positively infinitely large. And then, so the left-hand limit's negative infinity, the right-hand limit's positive infinity. So the overall double-sided limit of this function doesn't exist because the right-hand side and the left-hand side don't have the same behavior. They're not going towards the same infinity. You have a vertical asymptote that's doing this instead of this or this. Question. Cool. That's what I thought you would do. All right. Let's see here. So when you end up getting a non-zero number divided by 0, the real process is just to be like, plug it in. The top's going to be something that's either positive or negative, and the bottom's going to be something that is 0, but slightly positive or slightly negative. And your job is just to determine essentially the sign. Yeah. So if it's a one-sided limit, like approaching 10 from the left or approaching 10 from the right, it's always going to be an infinity of some sort. Now, I'm going to remind you, technically that means it doesn't exist. But we're still going to say we know it doesn't exist, but we know it doesn't exist in this very specific way, that it's getting infinitely larger than negative. Whereas the double-sided limits could not exist if the left and right hand side aren't doing the same thing. We'll look at another example. Yeah.
So,
So you have to, that's yeah, that's you need to know what they want. Typically in web work, they will, if you're using web work, it'll say things like you can put in INF or negative INF for infinity or negative infinity if that's your answer. Most people do accept those answers, but yes, I should really clarify. When I say that this limit is infinity, what I really mean is this limit as x approaches 0 from the right of cosine of x over x does not exist, but we see that cosine x over x gets large without bound, or infinitely large, as x approaches 0 from the right. So that is what all of this saying it equals infinity really is saying. We're saying the limit doesn't exist, but we know that the function has this behavior of getting infinitely large. Or in this case, we know the limit as x approaches 10 from the left of this function doesn't exist, but we know that the function is getting negatively very large as we get closer and closer to 10 from the left side. No one wants to write all that, so that's why we just say this instead. Let's look at one more example. I'm gonna have you all do an example. So I want you all to try this one. Try finding the limit as x approaches, sure, 5 from the left of x squared plus 1 over x minus 5 quantity squared. I'm going to tell you the answer is either positive infinity or negative infinity. I should have made negative x squared on top. Oh, well, too late for that. Don't have to show very much work for this kind of problem. So if I plug in a number slightly smaller than 5, again, I'm only really concerned about the being close but not equal to 5 thing where you might be dividing. So in the numerator, I'm just going to say I have what? 26. I'm really just plugging in 5. Just like I do for any kind of limit, right? The first thing I always do for a limit, if I can, I plug in what x is approaching, and then I see what I get. And if it works out, great. If it doesn't, then I do something. If I plug it into the bottom, a number slightly smaller than 5 minus 5 is slightly negative. You don't have to write it like this. You can do something else. I like to write 0 superscript. But then we are squaring, which means it's slightly positive. So I have a positive over a positive, which means this is going to be a positive infinity. On the other side, the limit as x approaches 5 from the right of x squared plus 1 over x minus 5 squared. Still getting 26 on top. And on the bottom, now I have a number that's slightly larger than 0 because I'm slightly bigger than 5 minus 5. And I'm squaring it, meaning it's still positive. So a positive over a positive is still a positive infinity. So in this case, we could say, since the left-hand limit and the right-hand limit are both having the same behavior, they're both growing infinitely large, that the double-sided limit as x approaches 5 from either side of x squared plus 1 over x minus 5 quantity squared is also positive infinity. It's a totally fine thing to say. Okay. Yeah. So here's what I would say. So let's do a kind of a sum up a little bit of our limit kind of our processes for dealing with limits. So limits. Now let me just hold a new piece of paper. Limits. What should you do? The first thing you should always do, just try play. So I should say, if you have the limit as x approaches a of f of x, if you're dealing with that kind of limit, and you're trying to see what it is, first thing you should do is plug in a. And whatever x is approaching. If x is approaching 3, plug in 3. And if you get a number, right, if you get like 2 over 5, or 0 over 6, 7 over 18, or 3, right, something that is just a real number, you're done. I should say you're most likely done. Some people, you can make up things that don't work so well. Like you can make, if it's I would say this is true generally. If you have a piecewise function, you should ignore this advice entirely. For piecewise function, this does not apply for piecewise functions. This is like if you just have a regular limit of a expression, right? You're not given this function that has 3 different pieces, and that's to find one. Okay. So then you don't always get something, right? A lot of the times we get 0 over 0. So if you get 0 over 0, what do? You do algebra. Meaning you could factor and cancel. We did a lot of that. Or maybe you might need to multiply by a conjugate and then factor and cancel. There's almost always some factoring and canceling. Conjugate. I will point out multiplying the conjugate, also good for trig sometimes. Like 1 minus sine x, 1 plus cosine x, stuff like that. And then the third kind of algebra thing we like to do is look for get a common denominator. Those are the typical algebra things we do if we have a 0 over 0 type of limit. Like, for example, if you have the limit as x approaches 3 of x squared minus 9 over x squared minus 7x plus 12. That's totally a factor and cancel, or I should say, that's totally a 0 over 0 type of limit. If you plug in 0, you get 0. If you plug in 3, you get 0 on top. You plug in 3, you get 0 on the bottom. And so for that 0 over 0 type of limit, you definitely would factor and cancel. Or for this one, right, you have the limit as x approaches 3 of the square root of, I don't know, x plus 13 minus 4 over x minus 3. You'd multiply the top and bottom. Oops, you can't see that, sorry. You multiply the top and bottom by the conjugate of the square root of x plus 3 minus 4. And then you would multiply it out, probably factor, do some simplifying, cancel some stuff. And eventually, after you do that, you would plug in 3 and get an answer. And I guess just to fulfill the list here, the third type is you have the limit as say, let's use 3 again. X approaches 3 of, sure, let's make it interesting. Sorry, my brain doesn't want to work. It's all right. 1, I will make it not interesting. 1 over x minus 1 over 3 over 2x minus 6. There's another 0 over 0 type where you need to get a common denominator. That's what I mean with these 3 kind of algebra things. You see these sorts of limits that are 0 over 0s, we typically go to this kind of stuff. Yeah. Sure. let me finish this here and then we can go ahead and do this problem. So then the third thing that might happen is you might get a not 0 over 0. Then that's the situation we were just talking about. If you get a not 0 over 0, there's only 3 possible answers. I should say, really, there's only one possible answer. The limit doesn't exist. But there's 3 possible ways of saying that and being a little bit more informative. So 3 possible answers: either the limit is positive infinity, limit is negative infinity, or the limit does not exist because you're looking at the 2 sides of the limit and the left and the right side don't match up. And your job really is just to plug it in still and determine what your sign is. So is the top part of the fraction positive or negative? Is the bottom part of the fraction positive or negative? Great. Positive or positive, positive, positive or negative, right? You know how to deal with positive and negative. So that's the idea there. And that's most of the list for dealing with limits when x isn't approaching infinity. There's limits as x goes to infinity because we're going to talk about it. So just to kind of address the question there, how would we deal with a limit where you had a common denominator kind of situation? So if I wanted to find the limit, I'm going to make it a little more interesting. Limit as x approaches 3 of 1 over x minus 1/3 over 2x minus 6. I'm going to get it. So if I want to subtract these fractions, I need a common denominator. Sorry, you can't see that. Let's try and keep it. So I'm going to say, well, that's going to equal the limit as x approaches 3 over 3x minus x over 3x. That's the whole reason I got a common denominator. So that I can write it as 3 minus x over 3x. That looks totally off kilter there. And then instead of dividing by 2x minus 6, let's say we're going to multiply by 1 over 2x minus 6. Feels like it's going to be a little easier. All right. I see some things that I wish cancel, but they don't quite cancel yet. I need to do a little bit more work. So I'm going to write this as one fraction. I'm going to factor out a 2 from there. So I really have a 3x times 2 times x minus 3. And from 3 minus x, I'm really going to factor out, actually, I really don't want to factor it out, but I'm going to factor out a -1. And I'm left with positive x minus 3. I will remind you that if you have things subtracting in the opposite order and you divide them by each other, they're always going to divide to be just equal to -1. So you could have just said, oh, I know that 3 minus x over x minus 3, they're going to cancel and leave me with a -1 behind. Or you could factor out the -1 and then see you have the same things and then they cancel. And then we plug in, right? We get -1 over 3 times 3 times 2. I'm substituting in the 3 for the remaining x's. And they get a number, -118. So that's how we deal with those things. And it's going to be, I would say it's going to be relatively obvious that we're going to use a common denominator because you're going to have a fraction plus or minus another fraction. They're not going to have the same denominator. So if you see that in the problem, it's probably a good bet that you might want to try that. Yeah. Mm-hmm.
Why is it now multiplied by 1 over 2
Well,
instead of 2x?
Well, because I'm multiplying by the reciprocal. So let me rewrite this for 1 second. So this here, that's going to be 3 over 3 minus x over 3x divided by 2x minus 6. But I would really encourage you to think of this as I'm dividing by the fraction 2x minus 6 over 1. So when you flip and multiply, what do we get? If I multiply, right? It's going to be 1 over 2x minus 6. Here's what I would encourage you to think about, because I see people make that kind of small error a lot. If you're dividing by a thing and you're rewriting it, you shouldn't be ending up multiplying by the exact same thing. right? Dividing by a thing and multiplying by the same thing is a different operation, unless the number is 1. Right? But dividing by 3 and multiplying by 3, not the same. So if I'm trying to simplify something like, 5/7 divided by 3, that should end up being 5/7 times, well, not 3, right? Dividing by 3 is not the same as multiplying by 3. I mean, I'm sorry, I'm not trying to harp on you, but you presented me with a good opportunity to talk about this. I should be multiplying by the reciprocal of 3. Or as I like to say, dividing by a number is the same as multiplying by its reciprocal. Dividing by 3 is the same as multiplying by 1/3. Okay. All right. Let's see. Do I have other things I want to say here? Oh, we should talk about that. Okay. So I'm trying to wrap up the limits here so we can start talking about continuity. So there's one other thing we should, I guess, talk about, which is limits where x is going to infinity. So we probably need to think about, for example, what's the limit as x approaches infinity of, let's say, 2x plus 5, x plus 1. You might know the answer to this already. Good. But let's think about what happens if we start plugging in very large values for x. So if I make a little table here, I'm never good at tables, are not my forte. So if I plug in, like x equal to 10, well, let's see, 25 over 11. Okay, great. A little bigger than, right, 2 and a little bit more. If I plug in 1,000, I'm going to get 2,005 over 1,001, which I brought my good calculator, so I actually have 2,005 divided by 1,001, 2.003 approximately. And let's do one more. If we plug in 1,000,000, I'm going to get 2,000,005 divided by 1,000,001. Now, I feel like I probably don't even need to use my calculator for you to recognize that 2 million and a tiny bit at the end divided by 1 million and a tiny bit at the end is essentially 2 million divided by 1,000,000, which is very, very close to 2. I'm going to do it just because I want to, because why not? 0.00005 divided by, I have too many zeros there? Maybe. 2.000003. Pretty good bet that limit's going to be 2. But how do we show it? Well, the way you're typically encouraged to show limits like this, at least before you learn other ways of doing it, is to have a limit as x goes to infinity or negative infinity of some sort of rational expression like this. You want to divide everything by the x to the highest power that occurs in the denominator. So if I divide everything by x, and then simplify, I have the limit as x goes to infinity of 2 plus 5 over x over 1 plus 1 over x. As x gets very, very large, everybody help me out here. What happens to 1 divided by a very, very large number? Super duper small. And how about 5 divided by a super large number? Also super duper small. So the things that are getting divided by x, those fractions are getting very, very small as x grows and grows and grows. So this is going to equal 2 plus 0 over 1 plus 0, which is 2 over 1, which is 2. A couple things here. Thing one, this is how you find the horizontal asymptote of this function. So the function f of x equal to 2x plus 5 over x plus 1 has a horizontal asymptote of y equal to 2. And you can totally graph it and see that as x goes out towards infinity or negative infinity, the function is going to get closer and closer and closer and closer to 2. From above. Yeah. So I would say, so here's where I'm not showing the work, but I'm going to, of using all those limit rules that we briefly talked about. So here's kind of the work I didn't do. So from here, we could say, okay, well, the limit of 2 plus 5 over x over 1 plus 1 over x is really the limit of the top part over the limit of the bottom part. But then the limit of a sum is the sum of the limit. So that's really the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 5 over x over the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x. Okay, so everybody, what's the limit as x approaches infinity of the constant 2? Right, if you're constant, doesn't matter what x is doing, right? I'm still just the same 2 I ever was. So limits of constants are always just the constants. I'm going to fit this in here, sure. Sorry, I'm just getting kind of squished in here. That's going to be 2. And here's the important question. As x gets infinitely large, 5 over x gets closer and closer to 0. So what we say is that the limit is equal to 0. Now I want to stress that doesn't mean the function ever equals 0. It doesn't in this case. It just means that we get really, really close to 0 as x gets larger and larger and larger. So it is totally correct to say that this limit as x goes to infinity of 5 over x, that limit is equal to 0. Because 5 over x is getting close to 0 as x goes further into 0. And in the same sort of way, the denominator, the limit of 1 is going to be 1, and the limit as x goes to infinity of 1 over x is actually equal to 0. And I'll stress one more time just because I think it's important. When you say a limit equals something, that doesn't mean the function equals that something. It just means the function is getting really, really close to that something. The function might happen to equal that something. That can happen. It's not allowed. It's just that what we're saying is that as x is doing this thing, as x is going this way and this way, the function is getting closer and closer. In fact, if you all can see it, what's the function of 2x plus 5 over x plus 1? Let's see if this works. I always make that mistake. Cool. There's our function, and there's our horizontal asymptote. And you can see that as we move way out to the right, the function's just getting closer and closer and closer to 2. And I guess I could zoom out if you really want to, but I mean, I don't really need to, I don't think. And as you move, also, we didn't take it, but you can take the limit as x goes to negative infinity and see the same sort of behavior, right? As we move to the left, oh yeah, and the y values are getting closer and closer and closer and closer to positive 2. They're never actually going to get there. They just get as close as you want. Other questions about this? Yeah. Yes, there's definitely a shortcut. We'll talk about that in just a second. Question over there. Oh, I plugged in x equal to 10. Yeah. So there is a shortcut that works for these kinds of things. Let me do 2 more examples first, and then we'll talk about the shortcut. So maybe 3 more examples. So let's look at this one real quick. Maybe we'll do 1 example, and then we'll talk about the shortcut. Let's say we have a limit as x goes to infinity of 2x squared plus 7 over 3x squared minus 5x plus 1. So if you know the shortcut, you already know the answer. But if we're going to do it the long way for just a second, we say it's the limit as x goes to infinity of, if I divide everything by x squared, I'm going to get 2 plus 7 over x squared over 3 minus 5 over x plus 1 over x squared. I skipped the step, right? I didn't show the step where everything is divided by x squared. I did the step after that where I'm simplifying it. So 2x squared divided by x squared is 2. 7 divided by x squared is that. 3x squared divided by x squared is 3. 5x divided by x squared is 5 over x. And 1 divided by x squared is 1 by x. And now the same sort of logic applies. All the things that are being divided by x or a power of x, those are all going to get super duper small since the denominator is getting super duper big. So that's going to go to 0. That's going to go to 0. That's going to go to 0. And we're going to be left with 2/3. So the shortcut that some people are referring to is that if you have a limit like this and the degree of the polynomial on top and the degree of the polynomial on the bottom are the same, right, they both have the same highest power of x, then the limit is the fraction of the leading coefficients. So the leading coefficient on top was 2, the leading coefficient on the bottom was 3, and the limit ended up being 2 divided by 3. So let me give you. It is possible to get. So someone asked, is it possible to get different values if we go to positive infinity versus negative infinity? And the answer is yes, but not for rational functions like this. So if you have just a polynomial divided by a polynomial, limit to the right and to the left, I should say the limit to positive infinity and the limit to negative infinity are always going to be the same for functions like this. But we will, I'll introduce an example where they're not the same in a minute. So let me ask you all to find or determine, or just say what the answer is on your paper, the limit as x goes to infinity of, sure. Let me think for a second here. 8 plus 9x minus 5x cubed over 2x squared plus 7x cubed minus 4. And I've written it out of order on purpose so that you have to think about what numbers are actually going to be dividing each other. Let me ask you all a question. Tell me on your fingers. What's the degree of the polynomial on top? Yeah, this many. And on the bottom, also this many. Right? The degree on top is definitely 3, the degree on the bottom is definitely 3. So if we were using the shortcut, we can say that the limit of this is going to be the fraction of those leading coefficients. Now, leading coefficient doesn't mean the thing you see first. It means the coefficient of the highest degree term. So the leading coefficient on top would be -5. The leading coefficient on the bottom is +7. So that's what the limit of this would be. It doesn't matter what order they're written in. We just have to look, pay attention to the highest powers. You could also have done all the work, right? You could have said, or you could have rewritten them in the proper order. But if you divide everything by x cubed, you can say that's going to be the limit as x goes to infinity of 8 over x cubed plus 9 over x squared minus 5 over 2 over x plus 7 minus 4 over x cubed. And then all of the things that are being divided by x to some power are going to end up going to 0. So I end up with -5/7. Okay, question. Right. Well, let's address that right now, actually. Question behind you. If x is doing what? Right. If x is going to infinity. If you have 5 over x and x is going to 1, limit's 5. So x has to be getting large. Or negative infinity. It works for negative infinity as well. So I want to point out for this one, if I changed it to -infinity, the result's still the same. I still divide everything by x cubed, and then 8 divided by a really, really, really big negative number, right? Because negative infinity cubed is a very large negative number. You're still going to get a very small result. So yeah, if you're dividing by something that's really, really big or something that's really, really negatively big, you're still ending up making that fraction very, very close to 0. Okay, let's look at least 2 other examples. What if I want to find the limit as x goes to infinity of 4x squared plus 7 over 5x cubed plus 8? I'm going to tell you all right now, the answer is not 4/5, because the degree on top and the degree on the bottom are not the same. So the shortcut way of answering this is saying if the degree on top is lesser than the degree on the bottom, Limit's going to be 0. I would encourage you all just to do so you can always do the work that I'm talking about, which is you can always divide everything by x to the highest power that's in the denominator. So here I can divide everything by x cubed. There's also a way of using the shortcut here that a student told me one time that I thought, oh, that's really slick, which I'll show you in a second. But you can divide everything by x cubed. If I divide everything by x cubed, I'm going to get 4x squared over x cubed, 7 over x cubed, 5x cubed over x cubed, 8 over x cubed. I guess I could have simplified. That's going to be the limit as x goes to infinity of 4 over x plus 7 over x cubed over 5 plus 8 over x cubed. And all the things being divided by x that's getting very, very large are going to go to 0. So 4 over x goes to 0, 7 over x cubed goes to 0, 5 is just 5, and 8 over x cubed goes to 0. And what's 0 divided by 5? 0. Question? Right, exactly. So 4x squared over x cubed reduces to 4 over x. I'm essentially canceling the x squared on the top and the x squared on the bottom. Or you could say I'm subtracting the powers. 4x squared over x cubed. X squared divided by x cubed is x to the 2 minus 3, which is x to the negative 1, which is 1 over x.
What if the numerator has a higher degree?
We're about to get there. So the one trick I want to show you that the student, I just thought this was like, you're clever. Okay, good for you. They were like, well, James, what if you just said it was this? What if you said, instead of writing that, I have the limit as x goes to infinity of 0x cubed plus 4x squared plus 7 over 5x cubed plus 8. Are the degrees the same? Technically, no, but close enough. Yes, the way I've written it. And so if the degrees are the same, the limit is the fraction of the leading coefficients, which is what? 0 over 5. Totally works. I don't personally love it. I think it's kind of tricky, but it works. But I would say I would always fall back on if you have a limit to infinity or negative infinity, and it's of a rational function, meaning polynomial divided by polynomial, you can always do this thing where you divide by x to the highest power that is in the denominator. And that hasn't been an issue so far because the denominator has always been the higher power. But in the next example, we're going to see that's not going to be the case. So let's look at something like the limit x goes to infinity of, what do I want to pick here? Sure. Let's say we have, sure, 5x cubed plus 7x plus 1 over x squared. Let's say negative 2x squared plus 4. And so now, just like with the previous problems, I'm going to divide everything by x to the highest power in the denominator. I'm going to divide everything by x squared. So check this out. I'm going to have the limit as x goes to infinity of 5x cubed over x squared plus 7x over x squared plus 1 over x squared. Again, you are welcome to bypass this step if you don't need to write it down. It's totally fine. And then we're going to simplify. So we're going to get the limit as x goes to infinity of 5x cubed over x squared is 5x. 7x over x squared is 7 over x. 1 over x squared is 1 over x squared. Negative 2x squared over x squared is negative 2 plus 4 over x squared. And then we're going to ask ourselves, okay, for the things being divided by x, those are all going to go to 0. But what's left? Got 5x right there. Where is x going to? Infinity. So what I have, and it's going to feel kind of weird to write down, but I have 5 times infinity divided by negative 2. What's 5 times infinity? It's 5 times bigger than infinity, which is still infinity, right? It's infinity. A number times infinity is still infinity. Or I should say a positive number times infinity is still infinity. What's infinity divided by negative 2? Negative infinity. The sign has changed. So it's going to be a negative infinity. On the other side of things, if we instead were looking at the limit as x goes to negative infinity, the work would be the same. Right? We would still divide everything by x squared. So this limit is x goes to negative infinity of 5x cubed plus 7x plus 1 over negative 2x squared plus 4. I'm going to skip this step. I'm going to go straight to there. The limit as x goes to minus infinity of 5x plus 7 over x plus 1 over x squared over negative 2 plus 4 over x squared. These things still go to 0. And then if x is going to minus infinity, I'm going to get 5 times negative infinity divided by negative 2, which is going to end up being positive infinity. Yeah. Yes, exactly. The reason why is because if you divided everything here by x cubed, you might be able to work it out. You might be able to figure out that the whole thing is going to positive, but it's a lot harder. Let me just show you. If we did divide everything by x cubed, I'd have 5 plus 7 over x squared plus this one. It might be actually easy to see. 1 over x cubed over negative 2 over x plus 4 over x cubed. And here's the problem. If x is going to infinity, the top's going to go to 5 plus 0 plus 0. And it goes to 5, whatever. But on the bottom, I'm getting 0 plus 0. And I don't know if 5 over 0, I don't know if that denominator is slightly positive or slightly negative. So I don't know easily if I have something that's going to positive infinity or negative infinity. So I always recommend if you have these kinds of problems, you divide by x to the highest power that's in the denominator. It's going to save you some strife. Yeah.
So what does the graph look like if we're doing it?
You asked the question I was hoping you would ask. So let's take a look. So first of all, here's what I would say. What's happening is, so back to, sorry, I know I just covered it up for a second. So back to what we wrote down for a minute. What we're saying here is that this is really talking about the end behavior of the graph. So as x goes way out that way, the graph, the y values take it out. So we're going to be going way down to the right, and on the other hand, way up to the left, because the limit as x goes to negative infinity of this is positive. So if you go left, you're going up. Here's what I would say about this graph. I know that the graph of y equals 5x cubed plus 7x plus 1 over negative 2x squared plus 4, that graph has a slant asymptote. We know it has a slant asymptote because it's a rational function where the degree on top is exactly 1 larger than the degree on the bottom. So it's essentially asymptotic to a slanty straight line. Before we do the graph, let me show you the work. It's not y equal to x, it's y equal to some multiple of x. Although I know it's going to be a negative multiple of x. I should say a negative multiple of x plus a constant possibly. So when you're finding a slant asymptote, I know it's nobody's favorite. When you're finding a slant asymptote, not that you probably are going to have to do this much, if at all. The way you find the slant asymptote is by doing polynomial division. I know, it's nobody's favorite. Especially with what I've made up here, it's real hot trash. Because when you multiply by negative 2x squared, you get 5x cubed. Negative 5 halves x. Nobody likes that. So negative 5 halves x times negative 2x squared is positive 5x cubed. And negative 5 halves x times 4 is positive something. Sorry, it's positive. Don't be an idiot. Positive. Negative 5 halves times 4 is what? Certainly negative. I think it's negative 20 halves, which is negative 10x. Don't worry, this isn't going to suck that much. We're done with the sucking part. Because now we subtract 5x cubed minus 5x cubed is 0x cubed. There wasn't an x squared, which is great. And 7x minus 10x, that's a minus sign. I know, right? It's a minus sign. It's the biggest minus sign ever. 7x minus 10x is plus 17x. Bring down the 1. But here's the thing. We're done. Because you can't, x squared has a higher power than x, so you can't divide that in anymore. We've gotten to the point where essentially this is the remainder. So our slant asymptote is y equals negative 5 halves x. Meaning if I was going to graph this thing, even though I don't really want to, if I was going to graph this thing, I would have a slant asymptote that looked like that. So -5/2 x is okay, it goes to the origin, and it's maybe looking like that. It's pretty steep. So there's my slant asymptote. And maybe, although I don't really know what the graph looks like because I didn't plan to graph this thing, maybe the graph does. I have no idea what the graph does. I'm gonna make it up. Maybe it does something like this. And then it does like that. And then maybe it does something crazy like this. And then back like that. But eventually, all the way to the left, it's getting bigger and bigger and bigger towards positive infinity, like the limit says it does. And all the way to the left. And all the way to the right, it's going down towards negative infinity. And in the middle, some crazy stuff happens that we didn't look for. Let's actually look at the graph just so you can actually see what it looks like, because my graph is not going to be excellent compared to. So let's see, what did we have here? We had 5x cubed plus 7x plus 1. We've already got. Over -2x squared plus 4. Oh, I wasn't so far off. Okay. So as you can see, it looks pretty crazy in the middle. If you zoom way out, it looks a lot like the straight line y equals -5/2 x. Like a lot like it. So this graph is asymptotic to that straight line. That straight line. Sorry, I'm getting myself my left and right backwards. That straight line for you guys, yeah. Yeah. Sure. Yeah, I know. Like where did we get to? So the original problem was just asking what's the limit as x goes to infinity of this quotient, and what's the limit as x goes to negative infinity of this quotient. So this we see is that we go way to the right, the function gets more and more and more and more negative. So the limit as x goes to positive infinity is negative infinity. And similarly, the limit as x goes to negative infinity is positive infinity. Right. So here's what I would say in general. And this is how it kind of works for any rational function. So I don't love that. So for the limit as x goes to plus or minus infinity of a polynomial divided by another polynomial, 3 things can happen. Thing 1, if the degree on the top is strictly less than the degree on the bottom, that was the second case we saw, the limit's going to be 0. On the other hand, if the degrees are the same, meaning the highest power at the top is the same as the highest power at the bottom, then the limit, I'm just going to write words here, the limit is the quotient of the leading coefficients. Quotient meaning fraction of the leading coefficients. And then finally, if the degree in the numerator is strictly larger than the degree in the denominator, then the limit is going to be either positive or negative infinity. And you have to do the work to see it. There's really like no set way of saying what it's going to be other than just dividing everything by x to the highest power in the denominator and seeing what happens. Question, comment, concern? Hard to read what I've written? Sure. So if something's hard to read that I've written, just say it. I know my writing is not perfect. I'm totally okay with it. So this last one here says if the degree of P is larger than the degree of Q, so P being the top thing, Q being the bottom thing, then the limit is either positive infinity or negative infinity. I mean, right, so quotient literally just means you're taking the top thing divided by the bottom thing, right? The quotient of two things is their fraction, is their one thing divided by another. But I saw another hand over here. Anything else I want to say about this before we move along? Oh yeah, someone asked about that. Explain how we knew. So I knew this function had a slant asymptote because the degree on top is exactly one larger than the degree on the bottom. Really, because if the degree on top is one larger than the degree on the bottom, then the polynomial division will give you something that is linear. When you divide something that has a power that's one bigger than another power, your quotient, the thing you get after you divide two things, is going to have a degree 1. I will point out, but I will not get into the fact that if you had something, for example, if you had a function like x cubed plus 1 over x minus 2, although we don't generally talk about it, this function has a parabolic asymptote. It's kind of weird, but if you graph this on Desmos, because I don't want to graph this, if you graph this on Desmos, and then you also do the polynomial division and you find the quotient after the polynomial. So if you do the polynomial division here, get myself into trouble. If you do this division here, you have x squared times x cubed minus 2, right? You're going to get some stuff here. I don't know exactly what it's going to be because I don't want to take the time to do it. But if you did this division, you would end up getting the parabola that this is asymptotic to, which is kind of weird. So there is such a thing as a parabolic asymptote. You should not worry about it. You should not concern yourself with it. No one's ever going to ask you about it. But you can have other kinds of interesting asymptotes other than slant asymptotes. But again, don't, like, you might just pretend I never said that because it's not important and never going to come up. So don't, if you're like, what the fuck is he talking about? Don't worry about it. It's not that big a deal. If you really care, come ask me an offset or something. Other questions? Not about parabolic asymptote. Okay. One more thing about these limits to infinity, and then we'll move on because we need to talk about continuity before we run out of time here. I want to talk about the graph of f of x equal to x plus 1 over the square root of 9x squared plus 1. Sure. So if I was actually going to graph this, here's what I would do. I would find the y-intercept by setting x equal to 0. I would get y equal to 0 plus 1 over square root of 0 plus 1, which is 1. If I want to find the x-intercepts, I would really just set the top equal to 0. You're really setting the whole function equal to 0, but when you're talking about a fraction, you want a fraction to equal 0, you really just want the numerator to equal 0. We're going to get x equal to negative 1. Vertical asymptotes, we look to see where you might be dividing by 0. In this particular situation, that's not going to happen because 9x squared plus 1 is always bigger than or equal to 1. Never going to equal 0. Right? If you try to get 9x squared equal to negative 1, nope, not going to happen. No real numbers will make that true. Imaginary numbers totally, but we're not dealing with them. And then finally, the horizontal asymptotes. Totes. Plural. Meaning we're going to get a different one to the left and to the right. Left and to the right. So if someone ever asks you, how do you find the horizontal asymptote? The general answer is you take the limit to infinity. Because the horizontal asymptote is just asking, is there something that the function is getting really, really close to as you go way out that way? So take the limit as x goes to positive or negative infinity. And we're going to do both. And we're going to we'll do the easier one. No, let's do the harder one first. Because if you don't do the hard one first. So if I want to find the limit as x goes to minus infinity of x plus 1 over the square root of 9x squared plus 1. So I want to point out, if x is going to negative infinity, is the numerator negative or positive? Negative, or super negative. How about the denominator? Let me ask you a different question. If you take the square root of something, what kind of thing do you get? Positive, right? Square roots of things are always giving you positive outputs. Okay. And we can take the square root of this because x squared will be positive, and then right inside we're safe, right? There's no domain issues here. Okay. So if I want to actually deal with this, I know my answer should end up being negative because again, either negative or positive. So let's see. Here's the process for dealing with this kind of thing. If we have the limit as x goes to negative infinity, what we want to do. Oh, I know what I should have said. What I want you to see here is we kind of, although not exactly, have a degree 1 thing on top, and we kind of, although not really the right language, to say we have a kind of degree 1 thing on the bottom, because the square root of x squared is kind of like x. So we essentially have a first degree over a first degree, which means we should get some sort of quotient of the leading coefficients action happening here. But how do we make that work? Well, what we have to do here is kind of deal with that x squared. So what we're going to do is we're going to factor out the x squared from inside here. I'm going to write this as x plus 1 over the square root of x squared times 9 plus 1 over x squared. Factored or divided out an x squared. And now I'm going to break this up. I'm going to break it up as the limit as x goes to minus infinity of x plus 1 over, I'm just going to rewrite this. The square root of a product is the product of the square roots. I have the square root of x squared times the square root of 9 plus 1 over x squared. Nothing too weird yet. Okay, now here's where things get weird. Now I know I kind of said this before. I kind of said the square root of x squared is kind of like x, and that's kind of like x, but it's not actually x. What is the square root of x squared actually equal to all the time? Absolute value of x. So what we have here really is the limit as x goes to minus infinity of x plus 1 over the absolute value of x times the square root of 9 plus 1 over x squared. Now, if x were positive, great, we just drop the absolute value. Because the absolute value of a positive number is just a positive number. But is x positive here? Certainly not. X is about as negative as it gets. So what's the absolute, let me ask you all, right on the board, so hopefully I'm just gonna, what's the absolute value of negative 6? Right, but how do I turn negative 6 into 6? I'm multiplying it by negative 1. That's how you turn any negative input in an absolute value into its corresponding positive output, is by multiplying it by negative 1. So the absolute value of x here, x is negative. How do I turn that negative value that x is into a positive number? I rewrite it as the limit is x goes to minus infinity of x plus 1. That's a minus infinity over negative x times the square root of 9 plus 1 over x squared. And I want to really, really stress here, since x itself is a negative number, negative x here, that is positive. X is like negative 1,000. So negative x is negative 1,000, which is 1,000. People get thrown off by this a lot, but I really want to tell you, I know it looks weird. I know I'm telling you the thing that has a negative sign in front of it is a positive thing. It is. If x itself, right, x all alone is negative, then negative x is positive. Because that wouldn't be, so because x is a very large negative number. But I can't just say it, right? I can't just say it, right, because I still have to write x. So, right, for example, if x is negative 1,000, how do I write down positive 1,000? I'm going to write down negative x. But x could be any large negative number. So I can't just pick one value and say it's 1,000 or it's 10,000 or it's 1,000,000 or 1,000,000,000, right? I have to actually say, well, for any negative number x, the negative of x is positive. Well, negative infinity is still right here, right? X is still approaching negative infinity. Mm-hmm. So here's what I would say at this point. Let's go back to what we said at the very beginning. We said that in this fraction, the top should be negative and the bottom should be positive. So here, if x is going to negative infinity, is the top still negative? Is a negative large number plus 1 still negative? Yeah. Okay, and if x is going to negative infinity, pretend it's negative 1 billion. If I plug in a very large negative number for x in the denominator, is the denominator still positive? It is, right? Because I have a negative times a negative big number, which is positive, and the square root always gives me a positive. So I need this negative sign here to make sure that the actual sign of my denominator is still what it's supposed to be. Right. So really what I'm doing though is I'm taking the absolute value in the context of, we know that the piecewise definition of the absolute value function is the absolute value of x is equal to x itself if x is already positive. You can throw them right there. Right? There's the right side of the absolute value graph. But on the left side of the absolute value graph, it's not y equals x. What is it? Don't be shy. I know you all know what it is. What's that line there? Y equals? Right, it's negative x. So if x is already negative, we have to say we have negative x to turn it into a positive. That's what we're doing. Okay, but now we can do our kind of divide everything by x to the highest power that's in the numerator, that's in the denominator. So I'm going to divide everything by x. So I'm going to have the limit x goes to minus infinity of x over x plus 1 over x all over negative x square root of 9 plus 1 over x squared divided by x. X over x is 1. 1 over x is just 1 over x. And the x over x here cancels, so I'm left with a negative. In fact, I should just cancel those. Square root of 9 plus 1x plus 1 over x squared. And now we're finally ready to actually find the limit. If x is going to minus big number, I'm going to get 1 plus, that's going to go away. And that's going to go away. So I get 1 plus 0 over the negative square root of 9, which is negative 1/3. So let me ask you all, if instead I was going to take the limit as x goes to positive infinity, what would you guess the answer might end up being? Sorry, I'm very deaf. Say it loudly. Positive 1/3. And what's the only difference between what we've done here and what we would do there is from this step to this step, we wouldn't have a negative x, we'd have a positive x because x is now a positive thing. So I should show the work. I shouldn't just be like, here it is. Okay, so if we were going to take the limit as x goes to positive infinity of x plus 1 over the square root of 9x squared plus 1. I'm not going to show all the steps. I'm going to jump to where we have the absolute value. So that's going to be the limit as x goes to positive infinity of x plus 1 over the absolute value of x times the square root of 9 plus 1 over x squared. Whoops, you can't see it all what I'm writing. Sorry. Let me know, please. Let me know if you can't see what I'm writing. Sorry. So then, in this case, since x is positive, the absolute value of x is just x. So that's going to be the limit as x approaches infinity of x plus 1 over x times the square root of 9 plus x squared. And then you can divide everything by x and get the limit as x goes to infinity of 1 plus 1 over x over 1 times the square root of 9 plus 1 over x squared. I will point out, I am actually dividing everything by x, right? When you divide this denominator by x, since it's a product of two things, you don't divide each factor by x. You just divide the whole thing by x and then cancel one of the x. Whereas if you have the sum of things, then you have to divide each thing by x. And then that's going to be 1 plus 0 over the square root of 9, which is positive 1/3. So this graph has two different horizontal asymptotes. It has a negative 1/3 to the left and a positive 1/3 to the right. And it looks like, it looks kind of crazy, but it looks like what it is, y equal to x plus 1 divided by square root of 9x squared, 9 plus 9x squared plus 1. Which, okay, it looks like a flat line because we've zoomed way too far out. But if you look at this here, oh yeah, if you look to the right, you're definitely getting y equals 1/3 is your horizontal asymptote. And if you look to the left, you're definitely getting y equal to negative 1/3 is your horizontal asymptote. Cool. There were some questions over here. Yeah, I'm happy to address those questions another time, but I don't think they're particularly pertinent now. So yeah. There are other limits to infinity we could certainly talk about, but I want to spend some time talking about other things. So I'm just going to leave you with this and ask you to think about this. So think about this. We're not going to address it right now. The limit. Oh, yeah. Think about this. Can't even see it. Okay. Think about the limit as x goes to infinity of the square root of x squared plus 6x minus the square root of x squared plus 6. Which I will point out is what's called an infinity minus infinity type, which is also an indeterminate form. Infinity minus infinity could be 3. It could be 0. It could be infinity. And maybe that infinity is infinity bigger than that infinity. It's kind of annoying. I will tell you though, if you do the work for this limit, which is kind of a pain in the butt, you do the work here, the answer is 3. I encourage you to work on that on your own. It's a good problem. You might need to, you definitely will need to use a conjugate. Sorry, so leave that for a second. Yeah, we don't need that. Okay. All right, let's move along. Okay, 25 minutes. 20. Not really. I have plenty of paper. Real question. Not really. Killing trees over here. Okay, so continuity. Oh yeah, I'm actually might have to go. Do I have more paper in here? I have more paper in my bag. Usually have like an extra thick stack of paper. So, or just not. I guess I could use the back side. That seems terrible when you're writing with pen. So continuity. Oh, I know what I was going to do. I was going to be efficient about things. I was just going to not try and draw pictures and talk about, use some notes I already have. So let's talk about continuity. So here is a nice function, piecewise function. I will point out when you're talking about continuity, a lot of your examples are going to be piecewise functions. So let's look at this piecewise function. It is f of x equal to x squared when x is less than 2, and f of x equal to x plus 2 when x is greater than 2. And I'll point out it's definitely not continuous. Well, I should say some language things. This function is continuous almost everywhere. And I'm still going to say it's not continuous. So when we talk about continuity, if we're saying a function is continuous, period, we really mean it's continuous everywhere. So this function isn't continuous everywhere, so we say it's not continuous. But really, to be more specific, I should say this function is continuous everywhere except for at x equal to 2. So this function is definitely continuous everywhere, but it's not continuous at x equal to 2. And here, I would say it's not continuous. And we can see that because f of 2 isn't even defined. Right? If you plug in 2, there's nowhere to plug in 2. It's not defined to be equal to 2 for the top piece. It's not defined to be equal to 2 for the bottom piece. So that's an easy way to see a function isn't continuous. If it's not defined at the point, not continuous. At that point, it means not continuous.
Is one of them considered an equal to, or has it equal to, does that like negate the other one, or like?
Well, they can't both be like you. It would be inappropriate to write this as x squared where x is less than or equal to 2, and x plus 2 where x is greater than or equal to 2. Well, as long as one of them was, then you actually wouldn't have a jump because that point would be filled in, right? Right now we have a hole at 2, 4. Right, they would, right. Now, maybe there would still be a vertical jump, so it wouldn't be continuous. Not in this case, but yes. So here, not continuous because the function is not defined. Here's a new piecewise function. F of x equals x squared when x is less than 2. So still the same left piece. And now the right piece is going to be x plus 3, so a little higher than x plus 2. But we are going to define it for x being greater than or equal to 2. Well, let's see what that looks like. Here's your x squared, right? The usual parabola up to the point 2, 4. 2, 4 is not a point on the graph, but it is where a hole is still. So I like to label it. And this point up here, the beginning of the other piece of the graph is 2, 5. Does this graph look continuous? Oh no, right? It does not look continuous at all. There's a big old jump. So if something doesn't look continuous, and I know that it's kind of subjective, a little, not really, but it's kind of, if you have an idea of what you think continuity looks like, you're right. Continuity looks like what you think it looks like. It looks like you drew the graph without lifting your pen off the paper. Does that look like that? No, it doesn't. Not continuous. Now, how do we more formally actually say it's not continuous? Well, what I would say here is that the limit at that point doesn't exist. Right? From the left side, the graph is approaching a value of 4. I should say, as x approaches 2 from the left, the graph is approaching 4. As x approaches 2 from the right, the graph is approaching 5. And since those values aren't matching up, we have discontinuity. So here, we can say that the function is not continuous at x equals 2 because the limit doesn't exist at 2. Specifically, the limit from the left and the limit from the right are not equal to each other, which means the limit as x approaches 2 does not exist. So this is the reason that the function is not continuous there. We have failed to have a limit that exists. Okay. So one way a function can be discontinuous at a point is for the function to not even exist there. Another way for a function to be not continuous at a point is for the limit to not exist there. And then the third and final way for a function to not be continuous at a point is for the limit to exist and the function to exist, but for them not to be the same. So let's look at this example. The function is equal to x squared when x is left of 2. It's equal to x plus 2 when x is the right of 2. So it's actually the same as this. It's the same function as this original function here we started with, except we're also now going to define the function to be equal to 7 when x is equal to 2. So it looks like that. And again, if you tried to graph this, okay, graphing. Oh, I have to lift my pen off the paper to jump up here to plot that point. Or even if there wasn't that point there, I still have to lift my pen off the paper to kind of go around that open circle there, but it is there, and then graph the rest of it. So just from an easy, like, we think about whether this is continuous or not, we're pretty sure it's not continuous, right? We drew it and we didn't do the thing we would have liked to have done. The formal rationale for why it's not continuous is, well, limit exists. The function, I should start with the function exists. And the limit exists, but they're not the same. So for a function to be continuous, the limit has to exist, the function has to exist. The limit as x approaches the point has to exist. The function has to exist at the point, and those things have to equal each other for a function to be continuous. So here is, and I'll say this in 2 different ways. Here's how we talk about continuity. Some people will say the following. F of x is continuous at x equal to c. Here's something you might have seen at this point. If this means when you see an if with two F's, it means if and only if. Meaning this thing is true. If this is true, then the other thing is true. And if the other thing is true, then this thing is true. It's a bi-conditional statement, meaning each thing implies the other thing must be true. So f of x is continuous if and only if the limit as x approaches c of f of x is equal to f of c. Now, I'll point out that's only the last thing I said of those three things, right? I said the limit had to exist and the function had to exist and they had to equal to each other. So here's what I will mention. This statement really encapsulates all three of those things at once. Because for these two things to be equal to each other, they have to both exist. You can't say that they're equal when they both don't exist. You can't say that it does not exist equals it does not exist. That does not continue. So if they both don't exist, it's definitely not continuous. Now, when I'm trying to show a function is continuous or discontinuous, I still go through the process. So even though this is what people sometimes, this is what books will say often, they'll be like, here's the definition. It's the limit as x approaches c has to equal the function. What we really want to do is a three-step process. So really, the better way of doing this is to say the following. F of x is continuous at x equal to c if and only if you meet the following three conditions. First, you check thing one, f of c exists. Then you check thing two, the limit as x approaches c of f of x exists. Often, especially for piecewise functions, this will mean checking that the left side and the right side have the same value. So that the limit as x approaches c from the left is equal to the limit as x approaches c from the right. Not always, but often. And then finally, if you've met those two conditions, then you can continue on and then check to see that they're equal to each other. If any one of these things fails, you're done. It's not continuous at that point. Question? So sometimes people give you weird examples. Like, let me just show you the following example. Let's say we had f of x equal to 1 over x when x is less than or equal to 2, and sure, 4 minus x squared when x is bigger than 2. I'm going to make a blanket statement. It's fairly true. Most functions are continuous on their domains, meaning as long as they're defined, they're continuous. Some examples: every polynomial ever. A lot of examples. Some other examples: sine of x, cosine of x. They're continuous everywhere because their domains are everything. Some more examples that feel less exciting: tangent of x. Tangent of x is continuous on its domain, meaning where tangent is defined, it is continuous. Now, I will also stress, tangent is not defined in a lot of places. If you look at tangent for a second, tangent, I can spell. There's a lot of places it's not defined, like it's got vertical asymptotes at x equals pi over 2. For example, whoops, what the, okay, geez, okay, help me out over there. Okay, x equals pi over 2, totally undefined. But tangent of pi over 2, you get division by 0. And any odd multiple of pi over 2. Right, so at those places, the function is undefined. So if I said, where is tangent not continuous? You could say, oh, it's not continuous at pi over 2, at 3 pi over 2, at 5 pi over 2, because it's not defined there. But it is also still correct to say that tangent of x is continuous on its domain. Because as long as it's defined, right, pi over 2 is not in the domain of tangent. You can't take tangent of pi over 2. So this function is technically continuous on its domain. Let me give you another example. Let me dock. And I will say it's kind of more of a language thing, really. So here's another example. F of x equal to the natural log of x. Let me ask you all. Does that look like the continuous function I just drew? Did I lift my pen off the paper? No, I did not. I mean, after I stopped drawing. Sure. Is it continuous everywhere? No, because it's not defined everywhere. It's not defined when x is 0. It's not defined when x is negative. But this function is certainly continuous on its domain. Because its domain, I don't probably have apostrophes kill me. I don't care. It's not a spelling class. Its domain is all positive real numbers.
When you were looking at the, planning of action, you were talking about like where it's not
Mhm.
continuous. Do you really-
Well, so here's what I would say. I would still say, even though I have said a thing, I've said that tangent is continuous on this domain, it still looks pretty discontinuous, right? There's a lot of jumps, right? You can't draw this without lifting your pen off the paper. But if you pick any point in the domain of this function, like pi or pi over 3 or something that's not an odd multiple of pi over 2, right? Like if I look at say that point right there, is the function continuous there? Yeah, because the function value exists and the limit from the right and limit from the left are definitely approaching that value. So any point you can pick the domain of this function, it's going to be continuous there. It's just that there's a lot of points that are not in the domain. So there's a lot of points where it's not defined. So there's a lot of places where it's not continuous.
Like explain like how to write out what's continuous
Yep.
and what's discontinuous. How would you write it for this? Like as an answer.
So it's annoying. So I would say the lazy way to say where this is continuous. So for f of x equal to tangent to x. So if I have f of x equal to tangent of x, I know I want to exclude every odd multiple of pi over 2. So if I was going to do that, well, I'd be like, okay, so I want everything from negative pi over 2 exclusive to pi over 2 exclusive. Union pi over 2 to 3 pi over 2. Union 3 pi over 2 to 5 pi over 2. And then I would use some dots. Like that. That's how, if I was trying to be not very like having to think too hard about it, that's what I would do. I'd be like this section, union this section, and then dot, 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 dot. Right. Because anyone reading that knows that you know what you mean. But if you wanted the more formal way of writing it, here's what people often do. They say, okay, well, I'm going to take like the main middle section, negative pi over 2, leave a little space, positive pi over 2, leave a little space. And then, so that's my main middle section. And then the next section is moved how much over? What's the period of pi? The period of tangent. It's pi. So basically what I'm saying is you can take that middle section, negative pi over 2 to pi over 2, and just shift it over by pi. And then shift it over again by pi again. And then pi again, and then pi again. So really, right, or people use k, but yeah, I'm going to add n pi and n pi. And say that n is an integer. Or if you want to be fancy about it, you can say n is an element of the set of integers, which is that fancy z thing. That means n is an integer. Z, fancy z, is the set of all integers. I don't know why they use z, but they do. Just like fancy r is the set of all real numbers. Don't worry about if your teacher's not. Don't worry about it. But some teachers are going to use this notation at some point. They're like, oh yeah, you should know this. So here you can see it a couple of times. But let's get to at least one example before that clock is killing me. I need to change the time on it. I think I'm like, oh, only 5 minutes. I've got 10 minutes. Okay. So for this example here, where is this function not? Well, I should say I would almost always default to asking where is this function continuous? But the question you almost always answer is, where is it not continuous? Because it's, excuse me, going to be continuous almost everywhere. Except for a couple points. It's definitely not continuous at 0. So not continuous at x equal to 0 because f of 0 is undefined. All right. Where's another potential candidate for discontinuity? Right. Wherever if you have a piecewise function, wherever you're switching from one piece to the next piece, that value of x where you're switching is a potential place where you might be discontinuous. So whenever you see a piecewise function, you should always be looking over at the x less than, x bigger than, and be like, oh, those are the places where it might not be continuous. So let's check out 2. So at x equal to 2, what's going on? Well, does f of 2 exist? So if I want to find f of 2, am I plugging it into the top piece or the bottom piece? Top. Okay, so f of 2 is 1/2. Great. Now the limit. So for the limit as x approaches 2 of f of x, I am going to have to look at a left and right hand limit because it's defined to be a different thing on the left and the right hand side of 2. I like to be thorough, so I would always encourage you. Sorry, I would always encourage you to look at the limit from the side you've already used to evaluate the function. So I know I used the top piece to figure out what f of 2 was. So now I'm gonna take the limit that uses the top piece, which is going to be the limit as x approaches 2 from the left. So the limit as x approaches 2 from the left of f of x, well, that's where I'm going to be using the top piece because that is where x is left of 2. Okay, how do I find that limit? What's the first thing we always do with the limit? Plug it in. Plug in 2. Don't plug in 1.9 or 1.999. Actually plug in 2. Right? Even when you're doing a one-sided limit, you still want to just plug in the value you're approaching, even though it's one-sided. So you get 1/2, which is not surprising. On the other side, if I want to find the limit as x approaches 2 from the right of f of x, that's going to be the limit as x approaches 2 from the right of, well, now I'm on the right side of 2, so I have 4 minus x squared as my function. If I plug in 2 again, not 2.1, not 2.001, actually 2, I get 4 minus 2 squared, which is 0. Does the limit exist? No. Is the function continuous? No. So if I were answering this question, I would say f of x is not continuous at x equal to 2 because the limit as x approaches 2 of f of x does not exist. I personally find it good to state why the function is not continuous. So if it's not continuous because the function doesn't exist there, you should say that. If it's not continuous because the function exists but the limit doesn't exist, you should say that. And then if they both exist and they're not equal to each other, you should say that. So if I was actually answering the question that was asked, which is, where is this function continuous? I would say, well, it's continuous everywhere except for 0 and 2. So it's continuous on the interval from -infinity to 0, union 0 to 2, union 2 to infinity. Everything except for 0 and except for 2. Would love to get one more example in for you guys before we finish up here. That one though. Yeah.
Zero in the first one, and like 2 in the second one. That like they're both gonna give you prime numbers.
Well, I wouldn't. No, we can't.
Oh, no.
You can certainly say plugging 0 in gives you an undefined. It makes the function undefined. Plugging in 2 does not make the function undefined. I can totally plug in 2. What do I get when I plug in 2? Well, actually, when I plug in 2, I get 1/2. So here's what this looks like graphically. Right, because there is a place I can plug in too. And I'm not starting like using backs of papers. Okay. I have backs, yes, cool. It's fine, great. So what I would say is that this function, so here's what this, come on, this function looks like the following. It's 1 over x up until 2. So at 2, we know we get a value of 1/2. So it looks kind of like this. 1 over x, 1 over x. Clearly not continuous at 0. It's not defined at 0. You got a vertical asymptote at 0. And then the other piece is 4 minus x squared when x is bigger than 2. So 4 minus x squared is this parabola that does kind of this, and then hits that point there. It continues on down in this parabola way. You could draw the rest of the parabola if you want. Like here's the rest of the parabola in case you want, like, right there's what it would be if we were drawing that. I don't really want that though. I just like, here's the rest of 1 over x if you really wanted it, but those are not actual pieces of the graph. The stuff I've drawn in blue is actually what the graph is. And notably, it's not continuous at 0 because the function is undefined there. And it's not continuous at 2 because the limit doesn't exist there. The limit from the left, the limit from the left, and the limit from the right don't match up. Okay. All right. So let me hit you with just one more example. Call it a day. Sure. Let's say I had the following. I don't love these examples. What's the one I want? I'll make something up. So let's say we have x is equal to piecewise function. Sure. X squared minus 25 over x minus 5 when x is, sorry, it's a brain kind of day. When x is not equal to 5. That's not really what I want though. Fine, we'll just deal with that. It's okay. And x is equal to 11 when x is equal. Function is equal to 11 when x is equal to 5. So where am I maybe concerned about continuity? 5, right? Okay, is this continuous at 5? So, step 1, what is f of 5? 11, right? They made it easy. They told us it was 11. Step 2, I want to find the limit as x approaches 5 of f of x. Now, here's the nice thing. Both on the left side of 5 and on the right side of 5, we have the same function. So it's easy to attack. We can just do it as one thing. The limit as x approaches 5 of x squared minus 25 over x minus 5 is the limit as x approaches 5 of x minus 5 times x plus 5 over x minus 5. The x minus 5s cancel. Oh, what should I have said before I did any of this? I should have said, I'm going to plug it in and see what happens. If I plug in 5, I get 0 over 0. So then I should do this. But really, do make sure you don't get in the habit of just going straight to factoring, whatever. Make sure it's actually 0 over 0. Because one time, someone's going to throw this at you. And be like, oh, it's the limit as x approaches 5 of x squared minus 25 over x plus 5. And you're going to start factoring and canceling. And then you'll be like, oh, but I could have just plugged in 5 and gotten 0 over 10, which is 0. So someone someday is maybe going to try and trick you like that. Don't let them trick you. Plug it in first. Okay, so then those cancel. And you plug in 5 and you get 5 plus 5, which is 10. Okay, so far, everything's good to go. The function exists. The limit exists. But then step 3, the limit as x approaches 5 of f of x, which is 10, does not equal f of 5, which is 11. They're not the same. So the function is not continuous. No. The limit as x approaches 5 of f of x does not equal f of 5. You have a point discontinuity. Now, what's interesting, what some people occasionally ask is, how could you move one point on this function so that it was continuous? Well, we could change this point 5, 11 to be 5, 10. That would make it continuous. All right, I would love to say more, but it's 11:51, so I should stop saying words and let you go on with the rest of your day. I'll intend to talk more about continuity on Tuesday and then start talking about the limit definition of the derivative.